So this is our second example in optimizing costs, and what we're told, this one has two parts. We'll look at the part A here first. We're told that a manufacturing company is responsible for designing a 500 milliliter can for diced tomatoes. We want to determine the dimensions of the can that will minimize the surface area of the can. Fair enough. We should start off by reminding ourselves that 500 milliliters is the same as 500 centimeters cubed. So if we're working with that 500 there, our dimensions are all going to be in centimeters. So first of all, we have to think about what kind of shape are we working with here. We got a cylinder. And what are we interested in about this cylinder? Well, they mention volume, and they mention 500 centimeters cubed is our volume, and we want to minimize the surface area. So we're going to need our expressions for volume and surface area of a cylinder. So what's the volume of the cylinder? Pi r squared h, right. Area of the base, pi r squared, because the base is a circle, times the height. And our surface area is going to be, yeah, Mike had it earlier, 2 pi r squared plus 2 pi r h. Now, what do these terms represent here? The 2 pi r is the top and the bottom. Okay, that's why there's the 2 out front. It's the area of the top and the bottom. And the 2 pi rh is the lateral surface, or the sides. I guess there's only one side because it's a curved surface. So these are the two equations that we have. Which one are we going to take the derivative of? Surface area, right? Because that's what we're trying to minimize. And we're given this piece of information here. We got 500 milliliters. So we know that our volume is 500. So let's put that in here. So if we want to optimize our surface area over here, we're going to take the derivative of this surface area function. But the problem we have is we've got two variables in here. So we want to express one of these variables in terms of the other variable. We want to get rid of either r or h. And it works a lot easier if we get rid of h here. So we're going to use our volume expression here to get a formula for h. So if I just solve this for h, I get 500 over pi r squared. And I'm going to substitute that into my surface area formula. 2 pi r squared plus 2 pi r, and h is 500 over pi r squared. And now I'm going to want to simplify this before I do the derivative. So I'll keep that first term the same, 2 pi r squared. And I notice that I can cancel out pi here. And I can cancel out one of my r's. So I'll be left with 500 over r. And 2 times 500, of course, is just 1,000. And I'll rewrite that 1 over r as r to the negative 1. Because that's a good form to take the derivative. So this is still surface area. So we're optimizing surface area here, so let's take the derivative. We get 4 pi r, and we get negative 1,000 r to the negative 2, and we want to set this equal to 0 and solve for r. So let's keep 4 pi r on this side. Bring the 1,000, the negative 1,000 over to the other side, and change it back to 1,000 over r squared. And then we can cross multiply by the r. So r squared times r is going to give us r cubed. And divide through by the 4 pi. And we can just take the cube root here, cube root, to get the value of r. So when I do that, I get r is 4.3. Okay, so that's going to be our radius. At this point, we would do the second derivative, sub in our value of r, and check to see that we actually had a minimum. We're just going to skip that step here in the interest of time, and then we'll go back to our height formula. We had height is 500 divided by pi r squared. So we'll sub in 4.3. And we're going to work all this out, and we get that our height is going to be 8.6. So what do we notice about our height and our radius? Yeah, the height is exactly twice the radius. So if we were to look at this can, edge on, our height would be 8.6. If our radius is 4.3, our diameter would be 8.6. So it would look like a square if we viewed it edge on. Diameter and height would be exactly the same. All right. Therefore, the can should be we'll say the can should have a radius of 4.3 centimeters and a height of 8.6 centimeters. Okay. Okay. So that gets us the minimum surface area. Now, part B here is where we start working with the costs. Okay. They tell us now that the lid and the base of the can are made out of a stronger metal that costs twice as much as the sides, or the side, depending on how you want to look at it. What dimensions will minimize the cost of producing the can? And we want to sort of compare our answer to what we found in part A. So we still want to work with, we're still approximately working with surface area, but now we want to look at factoring in the cost. So we're going to have a cost function here, okay, and this is going to be based on our surface area. So our surface area formula was 2 pi r squared plus what? 2 pi r times h, okay, was our surface area, where we said that this represented the top and the base, and this over here was the sides. Okay, the area of the top and the base, or the area of the sides. So now to get the cost, we need to multiply each of these expressions here by how much it's going to cost for that amount of metal. Top and the base by 2. Well, why do you say by 2? Yeah, I think you're right. Okay, Richard. Okay, here's what I would do. I would say, I would pick a variable. I would say, sorry, not a variable, a constant. I would say let A be the cost of, which one is cheaper here? The sides, okay? So I would take my expression for the sides and I would multiply it by A. If the top and the base cost twice as much, I would multiply that by 2A, okay? So A be the cost of the sides, and I'll just say 2A is the cost for, let's say, the base. Okay. So my area times my cost is going to give me, times the cost per unit area is going to give me my total cost. And then I can work with this function just like I worked with the other one. Let's see. Let's expand it out. We get 4a pi r squared plus 2a pi r. And let's sub in our expression for h, same as we did before, 500 over pi r squared. Sorry, I don't need a 2 in there. And rearrange this same as before here. So we'll get 1000a times r to the negative 1. Or again, I've canceled out pi, and I've canceled out one of these r's. Okay. So let's take our derivative here. C primed is going to be 8a pi r minus 1000a r to the negative 2. Set it equal to 0. And we can solve here. So 8a pi r equals 1000 over, 1000a over r squared. Okay. And I put a negative 2. I've moved it down into the denominator, so it should be a positive 2 now. Bring the r squared over to the other side, and we get 1000a. Sorry, as we bring it over, we're cross multiplying. So r times r squared gives us r cubed. We get 1000a up in our numerator, and then we want to divide this by 8a pi. Okay. And lo and behold, the a's cancel out. Okay? So just like Nick suggested way back at the beginning, we could have just multiplied one of those terms by 2 and the other one by, well, by nothing. Okay? Or, as I did here, we could have picked a value for the price, and that price just would have canceled out in the end. So it doesn't really matter. So now we just want to solve this thing for r, taking the cube root. And what we're going to get here is, I get 3.414, okay, for my radius. Plug this back in to the height. Okay, 500 pi divided by pi r squared. So 3.414 squared. And our height here is going to be 16 That's 695. Okay, I think. So now, what is the relationship between our radius and our height? It was a factor of 2 before. Okay. Now it's going to be a factor of, if we divide these two. Sorry? 4.89? Double check my math there for the height calculation. .500 divided by pi.
Yeah, 13.6 is height.
How much? 13.6?
13.6.
Yeah, and I wrote down 16, even though I've got 13 in my notes here. I don't know what I'm doing. Okay, so you divide it, and what do you get? Yeah. So the height is 4 times the radius. Okay. So why is it going to be 4 times instead of 2 times as it was in the previous one? Well, because we made one part of it cost twice, the material cost twice as much as the other one. Okay. All right. And that's where we're going to stop.